All right, here we are. Last lesson in the chapter, lesson 8.6, comparing linear, exponential, and quadratic functions. Core concept. We have our linear function with the equation of y is equal to mx plus b. We call this our slope-intercept form of the equation. It produces a straight line any which way on the coordinate plane, other than vertical. That's the only one that doesn't follow this form. Exponential function, y is equal to ab to the x exponent. The exponent is what's changing here. That's the variable part of this piece. And again, exponential is like a half curved kind of a line that increases pretty rapidly. Then we have our quadratic. So we've been working with these trinomials. This is a second degree trinomial. The curve line is called a parabola. And we've been working with that this chapter. So now we're kind of looking at all the different forms, noticing where the variable x is. We have our input domain values of x and our output y values. So in the first one, right, you have your input value here, multiply that to the slope, add or subtract the y-intercept to get the output. Here, your input is the exponent, so whatever the base is to that exponent as it changes times a. And then here, of course, a, x squared, so the variable is always squared, and then whatever your b term is plus the constant c. So moving right along. So the first thing we're going to do is be able to plot the points and then determine which type of graph it is. So let's give it a try. Page 273 in your journal. Let's see, I'll probably want to draw a line. I hate having to draw these coordinate planes myself. I'm not really good at it. Where should I go? Maybe here? I don't know. Okay, so you will be plotting the points. So 1, 2, 3, 1, 2, -2, 1, 2, 1, 2, 3, 4, -4, 1, 2, 3, 4, and up to 4 again, -1 and 8, so 4, 5, 6, 7, 8, and -5 and 8. So if you connect the dots, so to speak, wow, that's terrible. It is a parabola. So parabolas are quadratic. And there we go. Okay, number two. Doesn't matter where I put the x and y axis again. They're not straight, but we'll just do the same thing. There they go. All right, -3 and 1, 1, 2, 3, and 1. So there we go. -2 and 2, -1 and 4, 0 and 8, 1, 2, 3, 4, 5, 6, 7, 8, 2 and 14, so 8, way up, out of the world, okay, out of the ballpark. So we draw this curve. It goes extremely large very fast, right? And it's approaching 0 here, and we call this exponential. All right. Number 3. I'll just do something like maybe right in the middle. Just plotting the points. And connecting the dots. Wow, I cannot draw a straight line to save my life. Sorry. 4 and 0. 1, 2, 3, 4. Well, pretend like that's right there. All right, good. 2 and 1. Yikes. 0 and 3. -1 and 6. 1, 2, 3, 4, 5, 6. And then -2 and 10. Something like this. So what's happening here? Ooh, wow. Is again another exponential curve. Oh, well, I guess we don't need the word curve. It's an exponential function. Got carried away there. So I want you to do number 4 and answer the question. All right. Answer the question after you've graphed number 4. And I need to circle it like that. All right. Not sure why there was a blank slide. So the differences and ratios of functions. So this is going to make a lot more sense when we actually do this. But we do know that a linear function, the first differences are constant. So when we've examined tables, when we've looked at our tables, we know that when you have a constant rate of change, that's represented by the slope, and that is a linear function. For the exponential functions, we had a common ratio, and that was our geometric pattern, right? Our quadratic function, we have this thing called the second differences that are constant, and we'll have a little more examples in the future. So in all cases, the differences of the consecutive x values need to be constant. So as x changes by 1 or increases by 1, we are going to be describing how y is changing and then determine what type of a function is based on that. So let's get started. Here we go. It says the first difference for our exponential and quadratic functions are not constant. Okay, so when we do this, we're first gonna, the first thing we're gonna do is look to see if there's a common difference. And if there's not, we may look for a common ratio. And if there's not, we'll look for a common second difference. Okay, that's how we'll play this. So the example from your book, tell whether each table of value represents linear, exponential, or quadratic. So you just start examining them. So here's the solution. We look for the difference, right, between terms. So we know that this is going up by 1, this is going by -3. So the first differences are constant. That means it's linear, constant rate of change, linear function. Looking at B, 1 to 2 is adding 1, and then 2 to 4 is adding 2, and then adding 4, and then adding 8. It's not a constant rate of change for a common difference, but if you multiply by 2, right, multiply by 2, multiply by 2, multiply by 2, you get a common ratio. That's how you know it's exponential. Finally, I need to make this disappear down here. So it's kind of cut off here, but if you look and you find here, we have from -1 to -2 is -1. Then we have +1. Then we have +3, and then we have +5. So then we may want to look to see if there's a common ratio, and there's not. Then what we see is between -1 and +1 is +2. From 1 and 3 is +2. From 3 to 5 is +2. That's what we call the second difference right here. So since the second difference is +2, +2, +2, we know it's quadratic, and that's what we're going to be practicing on and looking for. So first determine that the differences of consecutive x values are constant. Then check the first differences are constant or consecutive y values have a common ratio. If neither of these are true, then check the second difference. So the first one, number 5, is from your journal. That's on page 274. But then number 6, we can maybe talk about that in class. Number 6 in your journal, you could try it, but you may see something that doesn't work. And I think that it's an error on their part. And I've done some further, looking into it. So I apologize for that, number 6. But I pulled a couple out of your textbook. So these are extra examples. You can choose to maybe write them down or not write them down. That's up to you. Okay, so here, -2 to -1, +1, +1, +1, +1. So our consecutive x values are increasing by 1. How are we going from 7 to 4 is subtracting 3. From 4 to 1 is subtracting 3. From 1 to -2 is subtracting 3. And finally, -2 to -5 is subtracting 3. We call this a constant rate of change, right? The first difference is constant. Therefore, it's linear. So number 5 is linear. All right. Again, -2 to -1, everything's going up by 1. So let's look here. 11 to 5 is -6. 5 to 3 is -2. 3 to 5 is +2, and 5 to 11 is +6. So it's not a constant rate of change. Could I look to see if there's a constant ratio? like, is 5 over 11 equal to 3 over 5? And it is not. So there's not a constant common ratio. So then I would look at the second difference here. From -6 to -2 is adding 4. From -2 to +2 is adding 4. From +2 to +6 is adding 4. I see that the second difference is constant, therefore it's following the pattern of a quadratic. Okay? And on part C, I want you to pause the video and answer the question, and then we'll work it out. So first off, I see that, we're increasing by 1, right? We're checking this on all of them, even though I haven't been writing it down. We know that the consecutive terms are increasing by 1. So then I'm going to look here and I'm going to see what the common difference is. We have plus 2.5. Then we're jumping right ahead to plus 15. We do not have whoa, and then it's getting crazy. So we do not have a common difference. Let's look for the common ratio, okay? So what would we multiply times a half to get 3, okay? So one way to find out is you take, if you recall from when we did this in our exponential chapter in the geometric pattern 1, we took 3 divided by 0.5. 3 divided by 0.5 is equal to 6. Test it out. Is 18 divided by 3 equal to 6? Is 108 divided by 18 equal to 6? And so on. What we find is there is a common ratio of times 6 times 6 times 6 and times, I don't know where to write it, times 6. All right, there you go. So we want to tell whether or not the data represents a linear, exponential, or quadratic function. Then it says we're going to write the function. Well, you should be able to write a linear function, right? If it's a constant rate of change, you calculate the slope, and if you see like a point like this, 0, 2, you should be able to put it in slope-intercept form. That's pretty critical I expect that of my 8th grade math students to be able to do it. So I would expect students taking Algebra 1 to know how to do that. So you may want to try that. If it comes up linear, see if you can write the correct linear. So if this shows up in big ideas from these points, we're going to do the example where we're just telling what they are. I don't think we're going to be requiring you to write the function this year. All right, so here we have, you can make them into a table, but you have consecutive x terms. So you have -2 to -1, that's +1, -1 to 0, +1, 0 to 1, +1, 1 to 2, +1. So let's see what's happening with our y. So -4 to -1 plus 3, -1 to 2 plus 3, 2 to 5 plus 3, and 5 to 8 is plus 3. So because it's a constant rate of change, this is a linear function. This is a linear function. If it's a linear function, you should practice writing what the function rule is. So let's check number 8. -2 to 1 for the x terms is +1, +1, +1, +1. Okay, so how about -9 to 0? That's +9. 0 to 3 is +3. Uh-oh. 3 to 0 is -3. And 0 to 9 is -9 is -9. So could I multiply something? To get 0, I would have to be multiplying -9 times 0, but then 0 times 0 is not 3, so there's no common ratio. So let's check the second difference. From +9 to a +3 is subtracting 6. From a +3 to a -3 is subtracting 6. And from a -3 to a -9 is subtracting 6. Since there's a constant second difference, this is quadratic. Okay, should be easy peasy. Let's keep going. Okay, Now we have a ball that's being dropped from a height of 305 feet. The table shows the height of the ball, blah, blah, blah. We weren't given the equation. So we won't even make the equation, but t represents the seconds. It's the independent variable. Tell whether we can model it by linear, exponential, or quadratic. So we're just doing what we just did before. So we can, double check the x going up by 1, by 1, by 1, by 1. Then is there a common difference? So let's see. So when I take 305 minus 289, I get 16. So we're going to subtract 16 here. So if I take 289 and I subtract 241, I'm subtracting 48 here. The difference here, so 241 minus 161, subtracting 80 here. Oh my. So then 161 minus the 49, I am subtracting 112. So is this a common ratio? So is 289 divided by 305. Ooh, that's a messy decimal. And then 241 divided by 289 is not the same. So it's not a common ratio. So let's check these second differences here. So we want to check the difference between, so if you're at negative 16 and you go to negative 48, we're going to be subtracting what? So we have 48 minus 16, 32. So I'm going to subtract 32. So the difference between negative 48 and negative 80 is minus 32. So it looks like our second difference appears to be constant. Nice. And this is modeled by a quadratic function. All right, there you have it. All of lesson 8.6 in its entirety.